project for Professor Kate Graham, Organic Chemistry. The date is August 1st, 2026. All right, so I was given an unknown substance, and this was given to me by my organic chemistry professor. I'm gonna go through the process of identifying molecules. The molecular code that I was given is C7H14O2, and we're going to, by the end of this video, be able to draw this molecule and know exactly the IUPAC name of this compound. So join me as we do this three-part process in identifying molecules. We're going to be starting with the IR spectroscopy, and what this does is going to identify the bonds and the functional groups that will be in this molecule. So, for example, if there will be an alcohol group, or if there will be a ester, maybe there will be an aldehyde. We're not sure in what form these oxygens are going to appear, so we need to first use IR spectroscopy. And second, we're going to use CNMR spectroscopy, which is another form of spectroscopy where we're going to identify the carbon environments. So where the carbon are attached to each other and where they are in the molecule. The last process will be the HNMR spectroscopy, and that is to identify the hydrogen environments and how many hydrogens are in the nearby carbon as well. So we'll get into that next, go a little further into each process. So before we get into the details about these processes, I'm going to describe how I got to SU. And for this calculation, I used a molecular formula. And I plugged the carbon and hydrogen values in, and I got a value of 1. So this means that the molecule can either have one ring or one double bond, and in this case, the 1 degree of unsaturation comes from the carbonyl C double bond. So as you can see, I just listed here the molecular formula, how I plugged it in, the calculation that I come up with, and you can just see here as well, this represents a carbonyl carbon in this case. Since there's, in my molecule, there's not a ring, so that means that there's going to be a carbonyl carbon. So the first process that we're going to look at is the IR spectroscopy, and this undergoes the process of being thrown infrared light. And when this happens, this excites the molecules, and this makes energetic movement in the bonds. When that happens, it vibrates them, it makes them bend or stretch, and many chemists refer to this sort of like a dance. And when this happens, we can pretty much record and recognize those specific dance moves, if you will, by certain energy frequency that they emit in wavelengths. So the CH bondage we can recognize here is at around 3000 wavelengths. And then we can recognize, I wrote it above the section so you can see there what it looks like. And 1750 wavelength is going to be a recognizable carbonyl carbon. So it's going to have a double bondage with O. And that gives us a clue to how one of the oxygens is going to be used. And you can see the other oxygen is here at a recognizable 1250, which usually represents a CO bond, a singular bond. So this is probably going to entail or have some sort of ester or and we're going to move on to the next type of results that we need to analyze in order to get closer to understanding which or determining which molecule this is. And here we ask ourselves with this result, what bonds are present? And as you can see, we've identified 3 major bondage types and 3 major functional groups as well with the signatures from the spectroscopy. Next, we're going to take a look at the second process. All right, so in the second process, we're going to figure out what is the chemical environment of each carbon. And the way that we do that is we're going to discover the density of the electron cloud, because the more electron density that there is, the more shielding and the lower ppm that we'll encounter. So as you can see, when there is a tighter hold between the molecules, for example, when there is CH present, this creates a tighter, more dense electron cloud. And in the other situation, there is less electron density, leaving it more deshielded, and this will cause a higher ppm. So that's why you have the carbonyl carbon at 170 ppm here, one thing that we can see as well is that there are 5 unique carbon signatures. And so if you recall, there are 7 total carbons, and that means that some of these signatures repeat themselves in the molecule. We're going to be putting together this information with the other 2 results in order to determine the location. And lastly, we have a process that is called 1H NMR spectroscopy. Here we're going to identify the hydrogen environments of each hydrogen. So what this will do, from what I understand, is that we're going to be focused more on the positive charges here and the effect of the electron cloud has on the proton's magnetic behaviors. So for example, we're going to take this molecule and put it into the machine, which is highly magnetized, it's a strong magnet, and this is going to create the need of the electron shield or deshielding to appear. And based on the reaction of this strong or weak electron cloud shield, we're going to have an increase or decrease in ppm. So in this case, these results, we can see that there is 2H, 3H, and 9H signatures. So this is going to be about why chemical shifts change, and this is pretty much just representing the idea that less electron density equals deshielding, which equals higher ppm. And basically, this means that oxygen pulls electron density away from carbon, leaving carbon more deshielded and pushes its signal to a higher ppm. The anisotropy also changes the magnetic environment around the carbon, which can affect shielding. And because this is a closed shell molecule with paired electrons, its multiplicity is 1. So this just describes the characteristics of the chemical shifts and the way that oxygen pulls the electron density away from the nearby carbons. The magnetic environments causing shielding and deshielding are the main concept in which we can then take these numbers and start to draw them. All right, so this is the fun part we've all been waiting for, to actually discover what molecule it is and draw it according to the clues that we have put together based on the test results of the 3 processes. We have the IR process, we have the CNMR process, and we have the HNMR process. Putting all this information together, along with the molecular formula, we're able to begin drawing what we think this looks like. So when we're drawing this molecule, the first thing that we want to remember is that there are going to be 7 C molecules, 7 carbons, and we're going to have 14 hydrogens. We're going to have 2 oxygens. One of them is going to be a carbonyl carbon, and one of them is going to be an oxygen that is attached to that carbon. So as we start to create this drawing, we can tell that there is also going to be a section where there is a carbon that has 3 more carbons attached to it. And you're going to be able to realize that based on the amount of hydrogens that this part of the molecule is representing. Since it's high hydrogen, on one end of this molecule, you can see that the other end of the molecule, there is a negative force, and on one end of the molecule, there is a positive force, creating a dipole effect in this molecule. So when I put all this information together with the molecular formula, I could figure out the structure of the unknown substance. And this spectroscopy gave me different clues that I could put up together and find out what the unknown molecule was. In the end, I realized that it was 2,2-dimethyl propyl ethanoate. And this does have another name, a more common name, and that is propyl acetate. But either way, when I saw the molecule in a 3D format and I looked at my drawing, I knew that it was in fact the same molecule. Here are the sources that I used. As I noted, the 3D molecule viewer from PubChem. This integrated visualizer is new and upgraded in order to help me to see and confirm that this is the correct IUPAC name and that this molecule does in fact look like the drawing that I drew in my notebook on the worksheet and then on the PowerPoint. So once I was confirmed with that, I also used the NMR chemical shifts from